Hi everybody, welcome to ISDTWF channel. This is the second part video covering my attempt to replace a MOS7501 CPU for the Commodore C16 with a 6502 CPU plus some logic add-on made with two 32 cells CPLDs. In part 1 I realized the first prototype, and that made the machine to boot apparently fine and also run some simple test programs. However, it was soon evident that the C16 had issues, and in a very random manner too. Of course, the first aspect here is my replacement circuit, but since I don't have any other TED based machine, I couldn't easily verify that the issues were really due to the CPU replacement bugs. So, to have the final proof, I sent both my replacement CPU and the TED chip to my friend Elder0010 that has both a C16 and a +4 in good working conditions. Finally, after crossing half Italy, my chips arrived. It was soon evident that the replacement GPU causes all the instability problems, as can be seen from these recordings that my friend sent promptly to me. Luckily, however, my TED chip appears to be fine, and that's what matters most, since I can try to fix my CPU replacement, but I couldn't easily find a replacement TED. Another issue with my prototype is that it's a bit too tall to fit into a +4, but I'll try to find a better solution to have shorter pin strips after I fix my logic design. While waiting for the chips to make the snail mail trip, I decided it was time for some upgrades on my C16. The first upgrade is on the RAM side, gone from 16 kilobytes of the original computer to 64 kilobytes. This will allow this machine to run +4 games and demos too. The only difference with a +4 would be the lack of the additional software in ROM, so I'll call this resulting computer as a Commodore -4. This upgrade is simple enough. First, look at the original memory circuit of a C16. There are two dynamic RAM chips, each holding 4 bits wide 16 kW addresses. These are U5 and U6. Then there are two address multiplexers, U7 and U8, that are needed to split the CPU address bus in two halves to feed the row and column address to the dynamic RAM chips. Notice how only 14 total address lines from A0 to A13 are needed to address a total 16 kilobytes of RAM, and that the two multiplexers have also two unused inputs that are tied to 5V supply rail. Now, if we put 4464 chips in place of the 4416 DRAMs, we have a total of 64 kilobytes available. But we also have to bring the two missing CPU address lines, that are A14 and A15, to the address multiplexers. So what I did is, of course, remove the original DRAM chips, but also both address multiplexer, since I'm confident I can do it safely. This will allow me to install sockets on all these ICs, and there will be no need to cut PCB traces, so the mod can even be easily reverted back to the original situation. Then I soldered two wires to a couple of vias that are connected to A14 and A15, and secured them to the PCB with a few drops of epoxy. After soldering the 4 sockets, the 4464 DRAM chips just go straight where the two 4416 used to live, and both U7 and U8 have instead one pin lifted out of the socket and soldered one to A14 wire and the other to A15 wire. Of course, we need to lift the two input pins that were tied to 5 volts, so U7's pin 2 and U8 pin 14. Where you connect A14 or A15 doesn't really matter, but I've chosen U7 for A14 and U8 for A15. The second modification is relative to the 5 volt power supply regulator. The original Commodore solution was to use a normal 1 ampere linear regulator, the ubiquitous LM7805, but since the current needed was too close to 1 ampere and also the power dissipated to drop the voltage from 9 volt input to the 5 volt output was too high, even when using an heatsink, they had to add a big power resistor to divert some current away from the regulator and bring it directly to the 5 volt line. The 20 ohms 5 watt resistor passes roughly 200 milliamps to the total 5 volt current and dissipates about 0.8 watts, and it gets hot too, along with 7805 that dissipates approximately 3 watts of power. I've decided to remove both the 7805 and the resistor and use a switching regulator of some sort in place of the hitmaker's duo. While waiting for a suitable regulator, however, I can power the C16 directly from a 5 volt DC supply. So as a 5 volt regulator replacement on the C16, I got this cheap USB charger adapter of eBay, advertised as a 3 ampere 5 volt output, and this costed, including shipping, less than €3, which is kind of amazing because this chip, if you get this LM chip of DG-Key, it will cost more than €5 probably. Well, I'm sure about this because I bought some new chips of this one. And so I suspect this is not the original chip, but we'll see later. And anyway, we need only 1 ampere, so this may be not 3 ampere, but I hope it's not even less than 1 ampere capable of current. So for the first test, I just removed the USB connectors and connected the 5.6 ohm 5 watt resistors, which will get a bit less than 1 ampere at 5 volts. I decided to test the regulator directly with the voltage input from the C16 board. And of course, initially, the output will go only to the load resistor. The first test is obviously just checking the output voltage with the dummy load. And it's close enough. Well, almost perfect. 4.97 volts. Now let's look with the oscilloscope at the output voltage waveform. As you can see, the ripple is not bad. This is almost 150 millivolts. Not too bad, but the frequency of this signal tells me the regulator chip on this circuit is not what is printed on its case, because this frequency is exactly 50 kHz, while the real chip should oscillate at 150 kHz. So the chip is clearly a fake. Definitely this is not a genuine LM2596, but a similar IC that has been remarked. In fact, the datasheet clearly states that the 2596 works with a 150 kHz switching frequency, which is 3 times what I've seen on this circuit. A quick search of a similar IC made me believe this is instead an LM2576 that works at 52 kHz, which is what I've observed with the oscilloscope more or less. The good news is that this is also a 3 ampere device, The bad news is that it was supposed to use a much larger inductor value than the one that has been used on this little circuit. However, since the ripple voltage is not really too big and the regulator is not going to work at more than 1 ampere, I've just added a few more capacitors both on the input side and on the output side to help getting rid of some of that ripple. However, I don't recommend using such a cheap regulator with a fake IC. You might not be as lucky as I've been here. So I've mounted the switching regulator in a more permanent way in place of the old 7805 device. This is a picture of the final modification of this C16 motherboard. To conclude this journey into linear regulator substitutions, this little replacement module would be perfect in place of the original 7805 in the C16, also when removing the power resistor. So now let's try to understand what's wrong with this design and find out if I can fix it. I reviewed the schematic and one first suspect error is the clock signal CLK that is used by U2 CPLD to latch the data bus on the I/O port memory accesses. In the prototype, I had connected this clock to the Phi0 input clock, but this isn't the right thing to do on any 6502 design, and memory accesses should be clocked by the Phi2 output clock, as I have done in this updated schematic. And then I found and corrected some mistakes I made in the first logic design, like setting the output enable on an internal node, which not only is not needed, but can cause a random external pin to become an unwanted output. The last design change was about the infamous gate input signal to the 7501 CPU. Not having any such working CPU at home, I had to ask for help on the CBM hackers mailing list. Luckily, a member of the list provided many scope traces of the signals of a working CPU, and that helped me a lot to figure out what the designers intended to do. Thanks so much, Gerrit. Of course, I think everyone knows that the 7501 CPU can be substituted with a MOS7510 CPU with a socket adapter and some kernel patches. In this web page you can see such an adapter. But the 6510 has no gate signal input, so why this new CPU was really needed remains to this day a real mystery to me. Anyway, to make the gate input work as intended, I needed an extra latch on the U2 CPLD, but as you can see in this image, it had no free resources. Luckily, the U3 CPLD had still plenty of resources free, so I decided also to change the hardware routing to move at least one signal from U2 to U3. And the only possible signal that I could move from U2 to U3 is the bus address 0 pin. So I updated the schematic moving B80 to U3, and to do that I also had to bring the CPU address 0 line to U3. However, U3 had only left the JTAG pins to add these new signals. This means that once programmed for the first time, it will disable the JTAG port. Luckily, the JTAG interface can be enabled by applying 12 volt to a VPP pin if needed. After that, the code for U2 has been changed to allow the gate input to latch the address enable control signal AEC and the bus read-write signal. The last issues I decided to address are related to the old PCB design that was not very good. In my attempt to make this adapter as small as possible, I had used an SMD socket on the top part and made a rather poor attempt at using regular pin strips mounted on SMD pads at the bottom. These not only made the first prototype a bit too tall, but turned out to be too unreliable because the SMD pads are not really strong enough to withstand many insertion cycles of the adapter. Here you can see that some of them were ripped off when I removed this adapter from a socket after a few dozen times during the various tests. The first revision of this adapter could be, however, successfully routed on a 2-layer board by using both an SMD socket and SMD-mounted pin strips. For this second revision, I decided I would still use the SMD socket that proved to be reliable enough, but switch to regular through-hole pins. This makes the adapter slightly larger, but it also led all my routing attempts to a dead end. So, after a few days of attempts at routing a 2-layer board, I decided to switch to a 4-layer PCB and have the routing completed in a couple of hours. This, of course, means the PCB will be a bit more expensive to be made. Then I ordered these new PCBs, and here they are when they arrived from the manufacturer. I started by soldering the two CPLDs. By the way, 4 layers PCB take really a lot of heat before the tin melts properly. This is even worse when 2 of the 4 layers are almost all solid copper, like I did in this case, to have one full layer for VCC and another for ground. On the other side, there are just a few resistors and bypass capacitors that need to be soldered before the 40 pins SMD socket. At this point, I soldered the needed wires to the JTAG connections to program the two CPLDs. For details on my JTAG setup, you can watch the previous video of this series that's linked in the description. By the way, in this case, the JTAG headers are not following any standard, but that allowed me to save some space and have an easiest routing. After programming both the CPLDs, I've soldered the socket and the pins. This second revision is better looking and also not as tall as the previous one. It still has almost the exact footprint of the original CPU. And the two CPLDs are now both on the bottom side of the little PCB. Let's see if it also works. I've installed back the original TED of this C16 and my adapter populated with an UMC branded 6502A, so a 2 MHz version, and for the initial test I'll just connect the computer to an old CRT television. So far so good. Notice the memory amount consistent with the 64K expansion. Well, okay, it's time to run some more serious tests. Now I kept the C16 running for a few hours, so I'm just gluing together some pieces of video recorded during all these tests. have not had any instability or crash of the computer this time. I have downloaded and run also the +4 port of Impossible Mission, as you can see. It's not too bad compared with the C64 game that still is my favorite game. However, many aspects of this port made it rather difficult to be played by me. Many things are slightly but enough different, like the robot movements, the jump distances, the jump heights, the platform positions, and the robot zapper distances. So I just gave up playing in it. In the end, my idea of using two 5V CPLDs to implement the 7501 features on a plain 6502 CPU proved to be feasible. Of course, there are already many other 7501 replacement solutions, but I still like doing retro hardware at least with only 5V parts. The same approach could be used, for example, to replicate the well-known MOS7510 CPU used in the C64. and even the MOS7501 CPU, which was used in the B-series computers from Commodore and was not produced in very large quantities, unlike the 6510. Unfortunately, as of April 2023, the ATF1502 CPLD with 25 nanoseconds speed grade can be ordered only with some months of delay. DigiKey is telling me that ordering in the mid of April will mean getting the parts shipped next August, which is still feasible anyway. However, this is the last CPLD family capable of running at 5V supply, for what I know. As a final test, I ran a demo. These fine pieces of programming art exploit most of the strangest features and bugs of their target computers. They use the CPU undocumented opcodes and implement fast loader methods to load the new parts from the floppy drive. I think that there is no better test for a replacement IC than to be able to correctly run a demo from start to finish. So this is the end of the demo and also the end of this video. I hope it was interesting and that you learned something. If you have any question, please use the comment section below. It's all for now. Have a nice time and thank you for watching.